the next method we consider is the method of forces. In forces, what we do is, let's say we have the capillary tube like this. This is the liquid filled up. And this is the meniscus. Here what we do is consider the weight of this liquid column being balanced off by the surface tension force. So the surface tension force is basically going to act tangentially like this, and since this is a two-dimensional view, if you see it three-dimensionally, we will have something of this format. It is going inwards. This is not radially outward. This is basically something like this. We have this and the forces are in this direction. So what we need to consider is the vertical component. Because it will be balancing of the weight, the vertical component will be in the upward direction. So if we consider forces, weight is going to be the volume of this section, which is pi r square, times the height of the fluid, h. This is the volume. This into the density will give us the mass, times g will give us the weight. The surface tension force this comes from the fact that this entire length is nothing but, because this is small r, this is going to be 2 pi r, the circumference. So we will have, say, SF is equal to 2 pi r times S. This is the net surface tension force. We only need to consider the vertical component of it. This angle is the contact angle theta. So the vertical component is going to be the resolvation of this net surface tension force along the vertical direction, which is along theta. So this is going to be nothing but cos theta. And these two forces must balance each other. So SF is equal to W. Therefore 2 pi r times S into cos theta is equal to pi r square h into rho into g. Pi gets cancelled, 1 r gets cancelled. What we have is h is equal to 2s cos theta divided by rho g r, which is same as we found out by the pressure method. Let us look at some questions that might arise if we change our setup a little bit. We found that h was equal to 2s cos theta by rho g r. Now, what if the capillary tube is inclined? The answer to this is the effects will be similar, the vertical height attained by the capillary will be the same. The only difference that will come is the length along which the capillary tube is placed. That length will be changing, which is, say if we have something like this and the capillary tube is placed like this, this height small h will be the same had the capillary tube been placed like this. Although this length, which is along the capillary tube, the length up to which the liquid is filling it up, this length will not be the same. This is what happens when the capillary tube is inclined. Now what if the tube length is less than the h which is computed by this formula. What if the length of the tube is less than this? It might be possible that you put a tube inside it and from your analytical calculation you derive h to be this, but the length of the tube which is outside is smaller than that. This is a very possible case. So in that case, what is going to happen is the liquid will come to the top of it. The meniscus will not remain same as the normal meniscus. So if we have a tube like this, and initially we had meniscus of this format, the meniscus which had initially the contact angle theta, which is the contact angle for water, this will not remain theta. When the liquid reaches the top, the meniscus will become something like this. Let me enlarge this. The enlarged view, say, is something like this. This angle, the new contact angle, say theta 1 is not going to be the same as theta. Rather, theta 1 will be greater than theta. This is what is going to happen if the tube length is less than h computed.